If you've ever battled through linear algebra, you've definitely learned some tricks for finding a determinant. But have you ever stared down this formula? This is the real deal, the master definition. I know, it looks like a beast, but it holds the secret to what a determinant actually is. And today, we are going to crack it wide open. So let's just ask it. What is a determinant, really? It's not just some number you calculate to pass an exam. It's this single, incredibly powerful value that tells you a ton about a matrix. It's like its DNA, revealing all of its deepest secrets and properties. And this is the master key, the Leibniz formula. Yeah, I know, it looks like a cat walked across your keyboard, but trust me, by the time we're done here, every single one of those weird symbols is going to make perfect sense. We're going to dismantle it together piece by piece. So, here's our plan of attack. First, we'll talk about what the determinant's identity really is. What's it telling us? Then, we'll dive right into that formula and decode its two key ingredients, these things called permutations and their signs. We'll see how to find those signs using something called inversions, put it all together for a 4x4 matrix, and then, most importantly, we'll talk about why this whole thing is a foundation, not a practical shortcut. All right, let's jump in. Before we even think about the how of the calculation, we have to get the why. What is this number actually telling us about the matrix? Well, this one little number is doing a ton of heavy lifting. First off, it tells you if a matrix is invertible. If the determinant isn't 0, you're good to go. It also tells you how the matrix scales space. Does it stretch a square into a giant parallelogram or shrink it down? And what happens if the determinant is exactly 0? Well, that means the matrix flattens space into a lower dimension, like turning a cube into a flat pancake. It's a huge deal, all packed into one number. Okay, time to go back to our formula. To really understand it, you only need to get two key ideas. First, there's a rule for picking numbers out of the matrix. And second, there's a rule that tells you whether to add or subtract the product of those numbers. That's it. So that first ingredient has a pretty fancy name, a permutation. But don't let that intimidate you. It's just a path through the matrix. The rule is dead simple. You have to pick exactly one element from each row and exactly one element from each column. No repeats. Think of it like placing rooks on a chessboard. Each one has to be in its own row and column. Each valid setup is one permutation. The second ingredient is the sign. For every single one of those paths we find, we have to assign it either a +1 or a -1. This is what tells us whether we add the product of those numbers to our grand total or subtract it. So, you find a path, you multiply the numbers on it, and the sign tells you what to do with the result. Okay, let's dig a little deeper into that first idea, the permutations. Just how many of these unique paths are there, and what do they actually look like inside a matrix? For a 4x4 matrix, the number of paths is 4 factorial. That's 4 times 3 times 2 times 1, which gives us 24. Yep, 24 unique paths. So that big summation symbol in the formula means we're going to be adding up 24 different terms to get our final answer. All right, so here's our playing field. A generic 4x4 matrix where each element is just labeled by its row and column. Our mission is to find all 24 ways to pick 4 of these elements, sticking to our 1 per row, 1 per column rule. So let's start with the most obvious path, the easiest one. It's called the identity permutation, and it just goes straight down the main diagonal. We pick the element from row 1, column 1, then row 2, column 2, and so on. That's path number 1. 1 down, 23 to go. But of course, they're not all that simple. They can get pretty twisty. Check this one out. For the first row, we pick from column 2. For the second row, we jump back to column 1. Then for the third row, we're over in column 4. And for the last row, we pick from column 3. It's all over the place. But look, it's still a valid path. We've picked exactly one element from every row and every column. All right, we've got our paths. Now for the second big question. How do we know if a path gets a plus sign or a minus sign? Well, for that, we use a clever little method called counting inversions. So what on earth is an inversion? It sounds complicated, but the idea is actually pretty simple. An inversion is just a pair of numbers in our permutation sequence that are out of order, meaning a bigger number shows up before a smaller number. We're basically just counting how shuffled our path is compared to the simple 1, 2, 3, 4 order. Let's just do one. It's easier to see. Take the permutation 2, 4, 1, 3. We go number by number from left to right. Start with the 2. Look at all the numbers to its right. Is any of them smaller? Yep, the 1 is. So that's 1 inversion. Next, the 4. How many numbers to its right are smaller? Well, both 1 and 3 are. That's 2 more inversions. Now the 1. Anything to its right that's smaller? Nope. So, we add them up. 1 plus 2 is 3. Since 3 is an odd number, the sign for this permutation is -1. Okay, this is it. We've got the paths, and we know how to find their signs. Let's put the 2 pieces together and actually calculate the full value for a couple of the 24 terms in our 4x4 determinant. And we'll start with our old friend, the easy one, the identity permutation, 1, 2, 3, 4, right down the main diagonal. So for 1, 2, 3, 4, how many inversions do we have? 0. It's perfectly in order, and since 0 counts as an even number, the sign is +1. So the very first term in our big sum is just +1 times A11 times A22 times A33 times A44. Simple as that. Now let's do our more jumbled up example, the permutation 2, 1, 4, 3. We know the path, now we just need to confirm its sign and write out the term. Okay, for 2, 1, 4, 3, let's count. From the 2, the 1 to its right is smaller, that's 1 inversion. From the 4, the 3 to its right is smaller, that's a second inversion. The total is 2. Since 2 is an even number, the sign is +1. So this term gets added to the total. And the term itself is A12 times A21 times A34 times A43. Now just do that 22 more times, add and subtract everything, and you've got your determinant. So now we know how it's done. But here's the big reality check. Is this how you should actually calculate determinants? If you have a 10 by 10 matrix, should you do this? Please, no, absolutely not. This quote really hits the nail on the head. This formula is the theoretical foundation. It's the deep down reason why determinants work the way they do. But in practice, it's a computational nightmare. A 4x4 matrix has 24 terms, which is a lot. A 10 by 10 matrix, that has over 3.6 million terms. Nobody is doing that by hand. That's why we have faster tools like row reduction or Laplace expansion. They're the shortcuts that are built on top of this beautiful but complicated foundation. And that's really the key takeaway here. The permutation formula isn't the tool you use every day. It's the blueprint that explains why the tools work. So I'll leave you with this question to think about. Now that you've seen the why, now that you know about this complex dance of paths and signs happening under the hood, how does that change the way you look at those simple shortcuts you've learned? It gives them a whole new meaning, doesn't it?